Hi, hello everyone. Welcome back to this deep learning video lecture series. In this lecture, we are going to discuss mainly the bias, another one important basic concept we need to understand how it is going to affect the model, deep learning model, what is the importance of this bias, and then the gradient descent algorithm we are going to discuss. So here I am going to cover mainly the definition part, what is a bias, and I will explain the importance of bias in a neural network, and then we'll see again what is a gradient descent and how this gradient descent works. And bias we discussed many times, like a artificial neuron will do the simple calculation like a weighted sum of all its inputs, and then it adds the bias term, and then that will be passed to the activation function, then decides whether it should be activated or not. So what is this bias? Why we need to add this bias to this weighted sum in this neural network? So that need to be understood, so that we can, because the parameter tuning, the set of parameters need to be tuning, hyperparameter tuning, the bias also, and mainly the two important parameters that will be updated in this back propagation, the bias and weights. So we need to understand this bias. So in deep learning, bias is an additional parameter that helps a neural network learn better by shifting activation function. So it allows the model to capture the patterns that would be impossible if weights alone were used. Okay, if you use only weights, and sometimes most of the time it would be impossible, okay, to capture all the patterns. So let us take one simple example, like if you take a linear equation and which is passing through this ordinate where y is equal to 0, like y is equal to mx. Okay, so suppose if I change the value m, that is a slope value, it may go like this. Okay, here origin remains the same. This is the way we allow this line, that is we allow this regression to learn the relationship between the, suppose like x and y. If you want to learn or identify or capture the relationship between these variables x and y, then this is the way, by changing the slope only. Like if you change the x value, it will keep on extending like this, but if you change the slope, and then we'll get the different lines with the different slopes. So this is the way we can, but it is still limited, its learning is still limited. So how that is, we can like extend the future, that is to capture the more complex patterns. Like suppose I want like this is the correlation, okay, because here I cannot change this, the y-intercept. If I change the y-intercept, so I can draw or I can identify the relationship which is like this, and even like this, even like this. So but if when the y with the y is equal to mx plus mx, we can only just change the slope. So if we have the constant, that is y-intercept, y is equal to mx plus c, this is y-intercept, so I can shift this origin, I can shift this, so that this is the way, that means the model is allowed to identify the relationship, exact relationships, or we allow to explore the complete such space. So that is how it is important in this. Similarly, the bias is used in deep neural networks. Here you can see here y is equal to mx plus c, one simple function, and if you change the value m, slope value, and then we'll get the different lines like this, where m equal to 0.5, this line represents the green line where m equal to 2 and this one, but here it is remains the same. Okay, we want to shift this point also, so that is the purpose of introducing this bias. Here you can see, and this is without bias, and if you add the bias, like here you can see there are three lines where the bias equal to -1, bias is 0, and the bias equal to 1. So we can shift this one, okay, that is by the function. We are shifting the function either left or right. Okay, so this is the importance of bias in neural network, deep neural networks. And similarly, you can, if you take another sigmoid function with this is a sigmoid function with without bias at 0, bias is equal to 0. So that means it's just only, we can see the changes here only, either this side or this side. This is remains constant. So, but if you add bias, if there is some bias, like if you add the term bias in this, then we would able to shift, like suppose here this is the equation. So by adding the bias, we can shift either towards this direction or towards this direction. So this is the importance of bias in deep neural network. Next, another important thing is a gradient. So gradient descent is an optimization algorithm which is commonly used to train the machine learning models and mainly neural networks. It trains the machine learning models by minimizing error between the actual value and the predicted values. That is, we calculate with the help of this loss function. So here you can see here the gradient descent, that is, we have selected the random point, the starting point, red color represents the starting point, and from this we started using this gradient by we are updating, keep on updating, as we discussed like the previous case. Like suppose if you want to update the weight based on the gradient, so W new, that new weight would be calculated as W old minus learning rate eta, and that is, let us say, delta x delta y by delta x. So the change of y with respect to the x, sorry, it should be here weight. Okay, this represents the weight and this could represent the error. Okay, let us say error. So in this case, so we have to calculate the gradient, and then we also use the learning rate eta. So then with the help of that, we slowly moves in the reverse direction, that is, we always subtract, and then so that is to we have to keep moving to the optimal solution. This is a optimal solution. So this is a way we can keep moving to this, and this is a plot I just plotted for a simple equation, that is y is equal to x square. So the goal of a gradient descent is mainly to minimize the cost function, that is loss function, the error between the predicted and the actual values. In order to do this, it requires mainly the two data points. That means how we can change this. So we have to change one, that is the direction and also the magnitude. So these factors determine the partial derivative calculations of a future iterations. It allows to gradually arrive at the local or global minima, that is a point of convergence. And these are like a different functions, like because always we represent this loss function, and if you look at the different functions, so I just plotted, that is only for understanding, to represent this 3D space, how a function would be. So these are the different examples of the functions. These are all some other different examples. These are also different examples of functions of a 3D, in the 3D space. So let us, as I said, the gradient means that the amount, the direction is one thing, and magnitude. So direction, which direction we have to, and also the amount, magnitude. Okay, direction and magnitude. So which direction, which amount. So here you can see a simple gradient visualization in the 3D space. Like suppose this is optimal, right? This is the position where it has an optimal solution. Let us say, suppose if you have started randomly from this point, then we, based on this gradient, that is, we have to always select the direction and amount. So every iteration, so that till we reach the optimal solution. Okay. So that is the way the gradient helps us in a deep learning to reach the optimal solution. So the same like the gradient 3D space, and this is a solution, optimal solution. This is a contour representation of different steps, that is to reach the global minimum. These are the different steps performed before reaching the global minimum. And these are like different contour maps for different equations, like sin of x times cos of y, and the gradient of this exponential minus x squared minus y squared, like this. That is just to understand the how the gradient, that is with the direction and the magnitude, keeps moving in every iteration to reach the global minimum. Here you can see the 2D representation of this gradient and how the learning rate and what are the incremental steps, that is before reaching this minimum cost, that is global. So the gradient descent algorithm is a mathematical optimization technique, that is we have to minimize the cost. So here you can see this gradient, and the initial weight would be selected, and then we take the incremental steps to reach this weight, and this is a line represents the derivative of the cost or the particular cost function. So the minimum cost is this one. So we have to, till we reach this, we'll keep on updating by using this derivative. So we have to compute the gradient, that is the slope, and this is the slope, the first order derivative of the function at that point, and make a step, that is move in that direction opposite to the gradient. So the opposite direction of the slope increases from the current point by alpha times the gradient at that point. So that is the way. And if you look at the gradient descent algorithm, it's just a two-step process. We need to compute the gradient and then update the weights and biases. So here we discuss mainly the learning rate. So learning rate, how it is going to impact, because I just explained, like suppose if you want to update a weight like wi, this is a new weight, and w, let us write this one. So w new equal to w old, that is we are going to update weight with respect to the weight, the gradient of the w, that is the derivatives we need to find out. So here learning rate eta, and so let us say this is loss function e, and with respect to w weight. Okay, so now here you can see the learning rate. This is a gradient and this is a learning rate, derivative a learning rate, and how this learning rate is going to play. So a learning rate in the neural network causes the model to overshoot. That means if high learning rate will causes the model to overshoot, so the optimal solution. So that if it causes the model to overshoot, then that leading to instability, divergence, and the poor performance, because the model may jump over the minimum point on the loss function and failing to converge properly and potentially oscillating widely around it instead of settling on the best weights. Essentially, it learns too quickly and may not generalize well to new data. Let us see just same cost function, like let us say the simple exam function y is equal to x square, and these are the initial parameters, and this is the starting point, and then the learning rate I set as 0.2, and the number of iterations are 10, and this is the way we reached to this optimal solution. Okay, so the learning rate, so this is stepwise learning, so that is decided based on this learning rate. So that is because the derivative is multiplied with the learning rate. And next, on the right hand side of this image, you can see where I gave this learning rate 0.99, high learning rate. You can see it's jumped over the optimal solution. That means it has come almost to this side. So that is a major problem. If we give the learning rate is very high, so overshoot may happens, then it jumps out of this. It's okay, so it has to take the many U-turns and coming to the optimal solution. That does not guarantee the accuracy. So next one is, in this case I just give very small learning rate. You can see this is optimal solution, and these are the steps, learning steps. Okay, 10 steps would be there. So, but it is not yet reached the optimal solution. Okay, so if more learning rate, then the overshoot may happen. That means it may isolate, like it will come down here like this. So that is the way the learning rate is going to affect this gradient. So in this case we discussed mainly the term bias, the importance of bias, and then gradient, and I've explained mainly how the bias, like weight and bias, are going to play the important role in this neural networks. The gradient is another important thing, because we discussed in the previous lecture like a vanishing gradient. That means when we keep on decreasing this, like W old equal to W new, that is a new weight, we are going to get by like W old minus learning rate times the derivative of, that is rate of change in the error with respect to the weight. So that is, we keep on decreasing, so then it becomes 0. Like then if it becomes 0, it vanishes. That means there is no update. That means W new becomes W old. There is no update, because minus learning rate times this one, and this gradient becomes 0, then this will becomes vanishes, then there is no update. So if a network without update, if you retain it, it will produce the same output, or okay, the same patterns or relationship would be identified. So that is a problem with the vanishing gradient. And we have another term called as a exploiting gradient also, that will be discussed in the coming lectures. So thank you for watching this video.